Sub techno. You just woke up, yeah. Definitely just woke up. Sounds so different. Yeah, it's just my morning voice. Alright. I'm on my Mac, so. Dude. Macs are so trash. I swear, Windows is better. I don't understand why people always back up Macs. I feel like I've been trying to be open-minded with the Macs. Oh, Windows is better. Alright. Since I'm on the Mac, we gotta go to the meta tagged, sort by frequency, past 6 months, and also I need that spreadsheet, which I need to get from the other computer. Yeah, Windows is better. I'll be right back. Alright. There's no roach. There's no roaches here. The hell are you saying? Where are we looking? Time is it? It's 11:10. It's not that late, but not that early. Alright, bet. We found it. Okay, so I can move this. Wow, that's something with the human. Like I wanna be. We can Log in. Log in. My lists. Frequency 6 months. Okay. All right. I'm gonna just start music, and I'll probably mute my mic. Spotify. Choking music. Okay, you guys can hear the music, right? Or you can, techno? Alright, cool. Cool. I shall mute them and study.
Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle Leetcode problem 339, Nested List Weight Sum. This is the most developer name title ever. Very nice, I think. After that, we'll go over two variants. Let's start. For once, the description isn't full of jargon and wordiness, so I'll read it. We're given a nested list of integers nested list. Each element wants depth that we this input. We'll YOLO with an example and try to figure everything out. Alright, here's our list of nested integers that's extremely nested. There's a list inside a list inside a list inside a list. My brain only works in one dimension, so the goal is to make it easier on ourselves and slowly unfold this spaghetti mess. I'll personally choose to work my way from left to right because that's how I attempt to read things. For our first element, we obviously have an integer of 1, right or wrong. Recall, each and every element in our input is a nested integer type. So, to know if it's an integer or not, we can invoke the isInteger function. We'd get back true. Great, what now? Well, according to the requirements of the problem, we're supposed to multiply this integer by its depth, which correlates with how nested the integer is. Here, our 1 is surrounded by one pair of curlies, thus at depth 1, what's 1 times 1? 1, let's add it to a sum variable. From the 0 to now 1. Moving on to the next element, this whole thing is also a nested integer type, whose underlying value is clearly a list, denoted by these two braces. Of course, technically, we wouldn't know that until we confirm with the isInteger invocation. This time it returns false, which is correct. It's indeed a list. From here, we can follow up with a call to the getList function, which retrieves the actual list field. To be exact, it returns a list of nested integers. Wait, this is the same exact type as our original input. If we know we want to unravel this whole mess list by list, why not repeat logic with inner list? That sounded grammatically odd, but the idea is worth trying. We'll repeat all the aforementioned logic with this sublist. For our first element, we have a nested integer. We call this integer, which returns true. Wait, like before, we'll multiply this number by its depth. What's depth again? Well, this integer 2, in the original input, was bounded by 2 pairs of curlies, so it's 2 levels deep. Back to the math, what's 2 times 2? It's 4. Let's add it to our sum. Afterwards, our second element, to no surprise, is also a nested integer. To figure out what type it is, we'll call the isInteger function, which returns a false. If it's not a number, it must be a list. There are surely numbers in this list. Let's once again repeat logic with inner list. Let's cut to the chase. What's integer 3 multiplied by a depth of 3? That's 9. We'll add it to our sum counter to get 14. You get the idea at this point. We'll move on to the next nested integer. That is a list. We'd invoke getList and execute order repeat logic with inner list one last time. Where on the first element, we have an integer 4 at level 4. To see this visually, it's encapsulated by 4 pairs of curlies. We take the product, get 16, and add it to our sum, which is now 30. Next up, we have a nested integer, where if we call it isInteger, we find out that it's correctly an integer type. We add the product of 5 times 4 of the 20 to our sum to arrive at 50. Now, this is somewhat new territory. We've successfully unfolded all the nestedness. Are we done? I wish, but not quite. Looking at our original input, I can't help but notice that we still have remaining nested integers to process, namely the 6 and 7. We have no choice but to go backwards. This action is deserving of another color. Back at level 3, we're actually also done with this nested list. If we keep iterating from index 1, we would have exhausted this whole list. We have no choice but to go backwards. Amazing, we're back where we need to be. Where were we exactly? Recall, we had recently repeated logic with inner list with this element, meaning we can pick up where we left off and move on to this nested integer. We call it isInteger, it confirms for us that it's a number, but 6 times a depth of 2. It's, silly me. I've forgotten this whole time. To actually operate on number 6, we have to call another function, getInteger. We can't operate off of the nested integer class itself. That's just not how things work. But okay, with this, we get what we expect, an output of 12. What's 12 plus 50? That's 62. With that, we're done parsing level 2. Let's go backwards once more. Let's continue our workflow where we had just repeated logic with inner list with this list. Therefore, on the way back up, we'll move on to the very last nested integer element. We'll politely ask, is integer? Yes, it is. We invoke getInteger. All right, we have it. We'll multiply by a depth of 1 to get 7. Let's reflect that in our sum variable. 69 is our answer. That's what we return. The big question remains, how do we solve this programmatically? Well, yeah, little do we know, we practically went through the DFS approach to solve this. Whenever I awkwardly said repeat logic with inner list via
Hello, and welcome back to the Cracking Thing YouTube channel. Today we're going to be solving Leetcode problem 339, nested list weight sum. We were given a nested list of integers, nested list. Each element is, we know the base depth is going to be 0, but every time, since everything inside of here is 1, at level 1, that means that its depth of this one must be 2, and this one as well, the elements inside must be at depth 2. So let's look at what that is. So there's 4 1s at depth 2, so that's 1 plus 1 plus 1 plus 1, that's going to be 4, and then it's at depth 2, so we get 8, and then we have 1 lonely 2 at depth 1, so depth 1 times 2 is going to be 2, and then we add this, we get 10, so that's where they get 10 from. What about 1, 4, 6? So we can see that the 1 is at depth 1, there's another nested parenthesis, so that means this 4 is at depth 2, and then the 6 is inside another nested bracket, so it's going to be at depth 3. So when we do the math, so 1 times 1, we're going to get level 2 times 4, this is going to be 8, then we get 3 times 16, this is going to be 18, and if we add these all up, that's going to be 27, so that's how we get our solution. So pretty straightforward and pretty intuitive to do it if you were to basically do it manually. But how are we going to do this in code? Because obviously we can't just do it by by just talking through it, we actually have to put up a solution. So what we want to do is we actually want to use a breadth first search for this, or you could use a depth first search. I prefer to use breadth first search because I don't want to worry about Stack Overflow, but we're gonna do it with the BFS. And the way that we're gonna do that is we're gonna pretend that we're gonna pretend that this is basically a tree where each level represents the, items that are on that level, and then we can traverse through the levels in a sort of breadth first search manner, even though we're not really building a tree or a graph. So what I mean by this is that we're gonna make a queue out of this data structure here that's given to us. And what we wanna do is we're gonna have our items in the queue, and we're gonna pop them one by one, from the left. So we're gonna pop our first item, and we're gonna see that it's actually a nested list, right? It's not gonna be just an integer, it's gonna be a list. So what we wanna do is, instead of processing this now and trying to do it, what we wanna do is actually just add it to the back of our queue, and then we'll process it when we actually get to the second level. So our queue starts out as 1, 1, 2, 1, 1, and then we obviously process this one, and then we put it at the back of the queue because we're gonna process it when we get to the second level. Then we process the 2, and we see that's just an integer, so we can add it times its depth to our final solution. So our answer, starts at 0, and then we're gonna add to it. Then we're gonna process this last one here. We're gonna pop it out of the queue, but then again, we're gonna see that it needs to be processed again. So we're gonna add the elements to the back of our queue, and actually they're not gonna be as a list. We're just gonna add, the values from the list. So that means that after our first iteration through the queue, similar to how we would, do a level or traversal, our queue will now have 1, 1, 1, 1, and now we're gonna have a variable to keep track of the depth we're at. So our depth variable essentially be equal to 2, because now we're on the second level, and we can now, since all of these are integers inside of the queue here, what we can do is just multiply them across. So we have 2 times 2, and then we have 2 times 2, 2 times 2, 2 times 2, and in the end we get 8, and then we add our 2 from the beginning, and we get 10, and that's how we're gonna solve it. Essentially what we want to do is we're gonna process our elements in the queue, and we're gonna, in the same way we do a level or traversal, we're only gonna process however big the queue is at that iteration. For every element in the queue, if it's a list, we just want to add it to the back of the queue for further processing on the next level, because obviously we need to unnest the values. If it's just an integer, we just want to add it to the answer, multiplying it by whatever the current depth is, and then we just do that for basically while, we get rid of all the nested items. So every time we see a nested list, we're not just gonna put the nested list back in there, because then we just get caught in an infinite cycle. What we want to do is actually just put the elements from the nested list into our queue as items. We don't actually just put the list back and get an infinite cycle. So if that's confusing, don't worry, we're actually just going to go to the code editor, we're gonna type this out, and it should be really simple. I think it's only about keep track start anything. Go on a select. Now we just need to say the key and say. So we're gonna see actually that's, and I got rid of it because it's kind of see with all this stuff here. The nested list class has has an is integer field method, has an add method which we're not actually gonna use. I'm gonna get rid of this. We don't need it. We have set integer. We don't need this. Get integer and get list. So this will actually get the values for us because it doesn't quite work like a normal list. So I'm gonna just paste back what we had so far. And okay, so if the current number dot is integer, so if the current number is an integer, then what we want to do is just add it to our result. So we're gonna say res plus equals to cur dot get. That will give us basically there's only integer to put that entire elements in there. Just not what we want. We're just gonna keep hitting the list, and then we're just gonna be putting it back and never actually getting anywhere. We're just gonna keep switching. If we just tuple and so we want to spread where we have to put that entire list back into the queue for further processing, and we want to spread out all the elements in there. So we're gonna say queue.extend. So extend, if you don't know, takes an iterable and places it at the back of the queue. If we just did append, we actually just append the list, which is not what we want. So actually remember we want to spread out the elements, otherwise we're just gonna get caught in an infinite cycle. Because we're just gonna keep hitting the list, and then we're just gonna be putting it back and never actually getting anywhere. We need to actually spread out the elements inside of that level. So that's why we use extend. So we're gonna say queue.extend cur.getList, so that will get the list, and that's all we need to do. So once we finish processing our level, obviously we then need to move on to the next level. So we're gonna say depth plus equals to 1, and that will increase the depth. And then we're up till we turn our result. We can see that it works. So syntax error is cool. And just submit this, and we can see that.
What's up? What's up, Kyle? This problem is an intro to the concept of recursion. It can be, but I did it with BFS. I guess I'll look into the recursion solution as well, but I don't like recursion. I like BFS way better. It makes more sense in my head. Am I studying? Yeah, I got an interview. Alright. Break's over.
that works. So what is the time and space complexity here? Well, we need to process all the elements of our list here, and we need to process them regardless of whether or not they're a nested list. It doesn't really matter. We still need to process n elements, where n is the total number of, items that we need to sum, and we just need to take into account the actual depth. But this is still going to be a big O of n solution. Remember, this is a breadth first search. Breadth first searches are usually a big O of n. And obviously, since it's a breadth first search, our space complexity is also going to be a big O of n. Where in the worst case we just end up storing all the elements which are on that first level. So basically, it wouldn't even be like a nested list. It would just be a list of integers. In which case, our queue is going to end up storing everything. So actually, we even initialize the queue with the entirety of the data structure that's given to us in the beginning. So obviously, queue is going to end up storing all of those elements anyway. So that is why it's big O of n in time and big O of n in space. Pretty straightforward. Not the craziest problems, although it's a quite popular space. Pretty straightforward. Not the big O of n in time and big O of n in space. Pretty straightforward. Not the craziest of problems, although it's quite a popular interview question, so you should definitely know this one. N in the time and big O of n in the space. Pretty straightforward. Not the craziest of problems, although it's quite a popular interview question, so you should. It's Q is going to end up storing all of those elements anyway. So that is why it's big O of n in the time and big O of n in the space. Pretty straightforward. Not the craziest of problems, although it's quite a popular interview question, so you should definitely know this one. And knowing the breadth first template is also good for you to know. Anyway, if you enjoyed this video, please leave a like and a comment. It really
Some variable. 69 is our answer. That's what we return. The big question remains, how do we solve this programmatically? Well, yeah, little do we know, we practically went through the DFS approach to solve this. Whenever I awkwardly said repeat logic within a list via these arrows, we performed recursion, breaking down our original input list by list, but also simplifying matters for my goldfish brain. And whenever I said go backwards, that meant we backtracked in the code, warping our workflow back to the upstream stack frames where we continue our DFS solution. As for the depth, we can pass in a counter variable that gets incremented on each recursive call. We start with level 1, pass in level 2 for the next recursive call, and then level 3 for level 3, and then level 4 for level 4. As to how we calculate our sum variable, we can't quite cleanly add to it how we did, and that's because our whole workflow is fragmented by different recursive calls. So what we'll do is initialize a local sum variable on each level. So on the first level, we have a sum of 1 at this point because of this element, but when we recurse, we'll initialize another sum variable, which on the first iteration will take out a value of 4, because remember, 2 times 2 is 4. After that, we have a sum of 9, and then a sum of 16. We move on to number 5, which remember we computed to be 20. We add that to 16 to get 36, and here's the tricky part. We return the sum of 36 so that on the backtrack, we can add it to our local sum of 9. Makes sense, right? The 9 came from this 3, and the 36 came from this list. We're working with the backtrack. How clever. Altogether, we get a sum of 45 that will return for the backtrack. We add that to 4, and to be very redundant, the sum of 4 came from this 2, and this 45 from this list. After that, we move on to the next element. 6 times 2 is 12, so we tack that on to get 61. We return this upstream, we add it to our 1 here, plus the last integer of 7 times 1, to ultimately arrive at our answer of 69. Amazing stuff. One last note, the way we utilized the API contract was logical, but it should be noted that we didn't use 3 other functions, which includes the constructor, add function, and the set integer function. These are extraneous, and only serve to confuse us, we can ignore them. The time complexity is big O n. Since we must process each nested integer one time, or technically twice. The space complexity is also big O of n, or to be more precise, big O of d, where d represents the depth. Examining our example here, we clearly have a maximum depth of 4, which correlates with the 4 stack frames in memory, hence the big O d. Alright, it's time to code. Okay, check out our method signature. We're given a list of nested integers as input as much as I want to. I can't recursively call this function since we need the depth variable. Therefore, let's write a DFS function that ingests both the nested list as well as the depth. Now, before I start implementing, let's pull the API contract of the nested integer, but let's get rid of the ones we don't need. Cool. In the code, first up, let's define our sum variable, 0 initialized. After that, we'll loop over our longness. Is this nested integer an integer? If it is, we'll add to our sum the number that can be retrieved with getInteger multiplied by the depth. Otherwise, if it's not a number, then it must be a list. In that case, we'll recursively call our DFS function, pass in the list, which we can get with getList, and the depth plus 1 because we're going one level deeper. Remember, this was the whole repeat logic with inner list. On the backtrack, we get back a sum. So let's add to this DFS iterations local sum variable. When this for loop is done, we can return the sum for the parent frame. One last thing to do, let's invoke our DFS function with the nested list input and a starting depth of 1. And let's not forget to return it. Great job. With that done, let's look at one of many variants.
Hello and welcome to figure out the depth and a list, the entries of which will be considered at the later stage. Towards the end, we take the list that we have right now and consider the entries 2 and 5 again at a depth of +1 m, which gives. Let's consider the list as shown here for the time and space complexity analysis. Let n denote the total number of nested entries or nested elements, that is either a list or a nested list with its sum. Again, we can simply use our implicit in the given list. That's
Great job. With that done, let's look at one of many variants. Welcome to the first variant, where the difference can be shocking, especially in an interview setting. What if you had total freedom to come up with your own schema? That's right, you have full authority to define your own implementation that represents a nested integer. And on that note, it doesn't even have to be named nested integer. Depending on what kind of individual you are, you'll either sigh a breath of relief or panic because of the ambiguity. Let's be realistic here. We can implement the whole nested integer class itself, but that is so time consuming. Although this is just a wrapper class over one or two fields, spending 10 minutes to code it is 10 minutes we can never get back in the interview. Personally, I'd go for a more minimalistic approach. How about something like this? A class named object for a lack of a better name. But overall, yep, it's pretty bare. There are no functions, just one field named value, whose type is either a list of more objects or a list of integers. But yes, this is really all we need. All the modifications to our code are implementation details, so let's just go over them. Alright, like I said, all the changes that we need are just ways in which we have to access our new custom data structure. Speaking of our new class, it's defined right here. Not only that, but our function signature takes it in, and yes, so does our DFS function. We'll go through a quick walkthrough and call out any changes as we see fit. On each DFS call, we'll spin up a local sum variable just like before. This happens on line 8. After that, we encounter our first source of contention. On line 9, we're now looping over a differently named input. It's objects now. Switching to the code, it'll be object in objects, right? Going through the motions of our loop. For the first element, how do we know if it's an integer type? Before, we called isInteger, but that's not a function that's available to us anymore. Instead, we can call the isInstance function to see if it's a number or a list type. Let's code that. That if is instance, and we pass in the object of interest, as well as the int to compare to. If this returns true, then we have ourselves an integer. We'll multiply this object by the depth and add it to our sum. Amazing. Moving along in our workflow, this means adding 4 times 1 to our sum, and then after that, adding 2 times 1 to our sum to get 6. We keep iterating where we have a list type now. Like before, we still want to access the underlying list value to recurse and repeat all the aforementioned logic, so let's do exactly that. Please note, we'd pass an incremented depth of 2. But wait one second, I kind of glossed over it, but to access the underlying list of an object type, we have to reference the value field. Let's reflect this in the code. That, instead of nested get list, it'll now be object.value. Everything else on this line stays the same. After this, there's this one last change. We'll call our DFS function with our new input. And that is the full implementation. Let's finish this workflow real quick. We start our loop and pass it in. Here, we repeat instance to the mix, turning this object being the same as before. For this you may breadth first search. For the wandering mind, why would we favor BFS over its DFS counterpart? To help understand, what if you had an input binary tree like such? Or in other words, a somewhat skewed tree. Yes, I'm aware this is not a nested list that we're used to, but bear with me here, I'm trying to make a point. The time complexities for either approach would remain the same, big O n. No matter which algorithm we pick, we'll process all 7 nodes. Let's note that down. The space complexity is a different story. Recall that I said that the space complexity for DFS is big O of D, where D represents the depth. In looking at our very much contrived tree, we would concretely accrue 6 stack frames before any sort of backtracking. Makes sense? If we used BFS, the space complexity would be big O of L, where L represents the level. In reverse order tree, the most popular level would be this one, for a total of 2 nodes. Our queue, as a part of our BFS algo, will have those 2 nodes at any given time throughout the algorithm. If we compare these 2 outputs, then in practice, can you see how the space complexity with BFS save 3 times the amount of space? Of course, if these numbers skyrocket at the given ratio, then opting for BFS could save a lot of compute resources. That's one of the motives to choose BFS, and now that we understand why BFS might be an attractive solution, let's actually solve this problem using it. If the past 5 minutes were confusing because I was rambling about tree data structures, then that's of objects. And for inspecting our other data structure, we also, for the next level, for explanation purposes, add it to our sum. The sum variable, let's return before I forget. Now, so long as our queue still has elements in it, or objects rather, there will be more to process. On each iteration, we'll loop for the number of objects that our queue contains. On each iteration of that, we'll pop from the left of the queue and insert it. Are you an instance of an integer? If so, we'll add to our sum.
I'm gonna go, everyone, if you guys are still here. But thanks for being here. But yeah, I'll see you guys. Thanks for being here, chat. Much love.